Hello. Hello, my name is Clark Robichek, and I'll be presenting a deployable origami-based telescope mechanism. The telescopes used in space are traditionally non-deployable, heavy, bulky, and very costly. The James Webb Space Telescope is a good example in that the primary mirror is a large, solid piece. Using a deployable design based on origami can improve space telescopes by greatly reducing the stowed volume while still increasing the aperture size. Larger aperture sizes are needed to improve clarity or see objects further away. And smaller stowed volumes lead to smaller payload fairing sizes and lower costs, leading to more missions. LiDAR telescopes lenses function by refracting the light through a membrane and focusing that light onto a sensor. These devices are used for climate studies, navigation, geological mapping, and more. Several requirements must be met to design effective LiDAR telescope lenses, including good circularity, aligned and planar panels when deployed, a good way to integrate the membrane, and a way to attach the positioning system. The hexagonal twist pattern shown on in the center here in the stowed state and on the right in its deployed state is a good candidate for this LiDAR telescope lens design because it has 1 degree of freedom, has high stability, good circularity, flatness when deployed, and a 3 times increase in area. This makes it a very promising design for the LiDAR telescope lens. But in order to use the hexagonal twist with rigid engineering materials, it must undergo one of many thickness accommodation techniques. The split vertex thickness accommodation technique is chosen for this application because it increases stability and optical area. The resulting mechanism after thickness accommodation is shown on the right, with the center of each panel removed so that light can pass through in order to function as a LiDAR telescope. There are 5 independent variables that determine the size and shape of the array. This modified hexagonal twist is a complex coupled mechanism. There are 12 internal vertices on the array. Each vertex is a spherical mechanism, as shown in this video on the top right. In a spherical mechanism, the angles between the panels correspond to links in a traditional 4-bar mechanism. These 12 spherical mechanisms are coupled together to create a single degree of freedom array. To increase performance, we completed an optimization routine of 5 independent variables of the modified hexagonal twist in order to maximize the deployed area while restricting the stowed volume. Once optimized, we created a variety of prototypes to validate and test the design and hardware. The final full-size prototype is shown on the far right. This work is novel because it's the first time that the hexagonal twist pattern is used as a deployable LiDAR lens. The separated panel design protects and secures the optical membrane. The mix of rigid hinges and membrane hinges restrict and allow motion in a tailorable way. There are many benefits to this design, including that it has a high deployed area to stowed area ratio. It has 1 degree of freedom, thereby simplifying actuation. The thick pattern is flat and stable in the deployed position. Positioning mechanisms can easily be attached to the underside of the array, and the embedded optical membrane is protected from damage. We conclude that this modified hexagonal twist mechanism is a promising design for use as a LiDAR telescope lens. Additionally, this work could be used in other space applications such as heat shields and solar arrays. I'd like to thank the NASA Earth Science Technology Office for funding this research, as well as all others listed here. Thank you very much.
So